So yesterday we did basic electricity. Today we're going to start on series circuits, resistors in series. Before I get started, I'm going to reiterate just a little bit over yesterday, especially since you wasn't here, Brent. So we've got our circuit, right, or our battery, which is our voltage source. We've got our resistor. All right. Voltage, remember, it's our pressure. It's what's pushing the electrons in the circuit. The circuit is the wire from the voltage source to the load and back, right? That's our one circuit. So voltage is our pressure. Resistance that is our opposition to the current. And then our current is our reaction depending on the voltage and the resistance, right? The flow of the electrons is going to be determined by the voltage and the resistance in the circuit. So it's like our reaction. All right. So give me a voltage. 50. Give me a resistance.
25 ohms.
25 ohms, he says. All right. Remember, Ohm's law, V is over IR. We know the voltage, we know the resistance, and we can calculate the current. We do that by, we're looking for current, right? Because we don't know what we cover up the I. That tells us that voltage is divided by resistance. That'll give us current. All right? So what's the current? 2 amps. All right? Current flow. Now, if resistance is the opposition to current flow, y'all don't answer. Okay? Brandon, if resistance is the opposition to current flow and I bring my resistance up, what do you think is going to happen to my current? It's going to go down, right? So they are inversely proportional. Resistance goes up, current goes down. We made a change to the resistance in the circuit. So current reacted to that and it went down. So our resistance went up, current went down. So if it went to 50 ohms, what would our current have went to? 1 amp, okay? He did that without calculation because he's seen that resistance doubled, current halved. Good. What if I've got 1.6 amps of current flow and I don't know the resistance in the circuit? How am I going to calculate that? We don't know the resistance, right? I showed them a little trick yesterday. I'm going to show you. If I don't know the resistance, I know, what do I know about this circuit? I know the voltage and I know the current, right? So if I know the voltage and the current, I'm trying to find resistance. I just cover up resistance. And that tells me that voltage divided by current will give me the resistance. So 50 divided by 1.6 gives me what?
It's going to be a little more than 25. So
Around 30?
31.
31? Okay. 31 ohm resistor, 1.6 amps of current, 50 volts. All right, what's going to happen whenever I change this to 75 volts?
The amps are going to change.
What are they going to do?
They're going to go up.
They're going to go pressure goes up, my pushing force, my voltage, if it goes up, my current is going to go up. We can calculate that. Now we don't know the current, right, because we changed the voltage. We can calculate that again by voltage divided by resistance will give us our current flow. What is it, Luke?
2.4.
2.4. All right. That's basically a quick recap on what we did yesterday. Feel good about it? All right. Now, what happens to my circuit when I add another resistor to it in series? In series meaning that the current path has to flow through both of those things. Those two resistors are in series, right? Well, this will be R1 and this will be R2. R1 is rated at 500 ohms and this one will be 1K ohm. Okay? Since this is the only path for current to flow, there is a few things that we have to remember. And this kind of goes back to like what I was talking about yesterday. The basic knowledge of it, all right? And just kind of think of it as in the simplest form that you can. Don't try to overcomplicate it. If I wanted to know what the total resistance, how would I find the total resistance?
Add those two.
You just add them together, okay? Because it has to go through both of them, right? So the total resistance is what?
1,500.
1,500. So RT, 1.5K ohms. All right. Now, in a series circuit, there's a couple of rules that we have to remember. First rule: current is going to be the same throughout the whole circuit. Anywhere in the circuit, it's going to be the same. Okay. So current is going to be the same. Why is it going to be the same throughout the whole circuit?
Because it's only got one path.
Because there's only one path, right? I can't be going, well, let's calculate the current on this real quick, okay? We've got 1,500 ohms of resistance, 75 volts. What's my current?
0.05 of an amp. 0.05.
0.05, so it'd be 50 milliamps.
We got 50 milliamps.
Is that right? Is that what y'all got?
75 divided by
1,500?
Yep.
And it's
0.05, so 5.
50 milliamps.
Yep. 50
Okay.
milliamps.
So we got 50 milliamps of current flow. Okay, I can't, in a series circuit, I cannot have 50 milliamps of current flow here and then 60 right here. Why can't I have 60 right here and 50 here? Because it's eventually going to run into it just like a traffic jam, right? It's going to slow it down through the whole thing. So there's only one path it can go, so current is going to be the same throughout the whole circuit. So my current in R1 is going through R1 is what?
50 milliamps.
Huh?
50 milliamps.
50 milliamps. What about R2?
50 milliamps.
50 milliamps through the whole circuit. Total resistance, 50 milliamps, okay? Current is the same through the whole circuit. Now, what is going to be different at different points of the circuit? Your resistance will be, that is true, but your voltage. Your voltage, so because you've got two resistors here in series, they're going to share this applied voltage, okay? One is going to take up more of it than the other. Which one do you think is going to take up more of it than the other? R2, because it's more resistance, okay? That means there's going to be, think of it as a voltage drop. Remember, voltage, the definition is a difference of potential, okay? So, think of it this way, what is the difference in the voltage potential here and here? That's how much voltage drop the resistor has, okay? So, let's just do this math. How many volts do we got at this point right here? 75. 75, all right? Now, what do we know about R1? We know the resistance of it. What else do we know about it?
How much current it has?
We know the current, but we don't know the voltage drop that it has, okay? But guess what? We can find it because we know the resistance and we know the current. So, we take the resistance, multiply by the current, that'll give us our voltage drop. And remember, this is in milli. So we gotta convert it to 0.05. 25 sounds right.
25,
Wait, 75 times
Yeah, that sounds right.
500.
25.
Oh, yeah, not 500. No, I messed up.
Be 500. Be 0.05 times 500.
Yeah.
And it comes out to be 25? Okay? So, if this is dropping 25 volts, how much voltage do I got right here? 50. Alright? Now, think of a multimeter, and we haven't been through meters yet, but remember, voltage is just a difference of potential. I've got a potential here, I've got a potential here. The difference is the voltage amount. Alright? My meter, that's how my meter reads. Your meter has got two leads on it, right? The black and the red. All your meter, when it's set on volts, all it does is it says, how much voltage do I got here? How much voltage do I got here? And then it tells you the difference. So if this one reads 10 and this one reads 20 or 30, this one reads 10, this one reads 30, what's my meter gonna read? 20 reads the difference, right? So I measure across this resistor, what's it gonna tell me? 25, the voltage drop of the resistor, okay? So, cool, right?
Yeah, I mean, I just would have guessed 50, I don't know why.
Well, no, because you got 75 here and you got 50 here.
Okay, I got you now.
All right, so now this one, what do we know about this resistor? We know the current of it, right? And we know the resistance.
Yep.
All right, so what's the voltage drop of it?
50.
50.
Yeah,
We know it's 50 because what's the voltage at this point right here? 0.
Oh.
0 right here on the negative side of the battery. And this is just a wire from this point to this point, so we know right here is 0. So what's the difference? 50 and 0? 50, okay? Here's another rule for series circuits. Actually, this is for all circuits, parallel combination series. The applied voltage will always be dropped throughout the circuit. Will always dropped, okay? It's always going to drop across the circuit. We'll build this out here too here in just a few minutes. So, what happens if the entire voltage is going to be dropped? And I change, what happens if I change this resistance right here to 1.5K?
Then you had,
You'd have 0 voltage, and your current would also be.
It changes everything because it changed the current, right? Which is going to change the voltage drops across the resistors. But you're going to see that that rule that I just told you, the entire voltage will be dropped, is going to stand true. And if you think about it, negative is always good. Well, not negative isn't always going to be 0, but the negative post, think of a battery, is always going to be 0. The ground, right? The ground's going to be 0, always. If it's always 0, no matter what I'm putting between the hot and the ground, it has to be dropping it completely, right? Because it's always going to end up back to 0. Has to, if you think of it that way. So, what happened? I changed this resistor to 1.5K. I've got some big differences. Actually, this is going to be 75 still. What happened? It's going to change my current, right? What's my total resistance now? 2,000. So what is my current flow? $33.
0.0375. So
37.5.
yeah, 37 and 37. 375 microamps for the beat.
No, it'd be milli. It'd still be 37.
0.0375.
0.0375. which is 37.5 milli, okay? Alright, my current went down because my resistance went up. Now let's see if our Ohm's law is still true. This one, I know the current will be at, what is the current in this resistor? 37.5. What's the voltage drop? Luke?
We're going between R1 and R2 again?
Yeah, I wanna know what the voltage across R1 is.
0.15. That's what I read. You do 75 divided by 500, correct?
No,
I'm sorry.
we're looking for voltage, right?
Oh, okay.
Looking for the voltage drop, so we cover it B, so it's current times resistance. We can't do 37.5 times resistance, right? We gotta do what? 0.0375 times 500.
18.75.
18.75? Is that right? Okay. It's dropping 18.75. So what's my voltage on this side of the resistor now?
56.25.
56.25?
Yep.
You can go ahead and do the Ohm's law for this, but we know it's gonna come out to 56.25, right? Because right here is 0. Go ahead and do the math on it. 0.0375 times 1500. 56.25. Okay. So the law stands true, right? Drops completely. The resistance changed the current, it changed the voltage drops, it makes all the proper, it reacts to the changes that we make and the laws stay true, okay? So real quick, let's build I'm gonna draw out a circuit here. We will do like we did yesterday, right there, but we're gonna calculate it, what it's gonna come out to be, and then we'll go out here and build it, and then take the measurement readings on it. All right. So, $75 is the applied voltage, all right? So what's my total resistance? 1500. Okay. What's my current?
50 milliamps.
Huh?
50 milliamps.
15 milliamps? 50? Are we back to what we was just doing a second ago? Let's change this up a little bit. Let's go 600 ohms on that one. So what's my total resistance now? 18. Now, what's my current?
Uh, 41.6 milliamps.
41.6 milliamps. All right. What is my voltage drop of resistor 1? 12.48. Okay. I'm just gonna say 12.5 voltage drop. You see that? So what's my voltage on this side?
62.
62 and a half. Right? And then I know my voltage drop from here to here is gonna be 62.5, right? What happens if I read from here to here,
So we just,
It's gonna be 75.
the total, right?
Now, obviously, this is different with AC, the whole, how you can go ahead and say that it's zero past the
No.
second resistor.
No, yeah, in AC it is alternating,
Right.
but there still is a zero. Whenever you think of it, this is why we learn this in DC, because it's easier to think of it that way, because in your AC, you're like, well crap, this side's zero, and this side's zero, and this side it flips, right? But the Ohm's law formulas still stand. They still work the same. If you just think of it as this way, even if you're dealing with AC, think of it in your head this way, because if you do it the other, you'll be confused. Okay. So, did y'all do the Ohm's law calculation for, we got 41.6 milliamps, did y'all multiply it by 1200 ohms and see if it come out to 62 and a half? Should be somewhere close to it anyway.
I got 49.
I got 49.99.
49.92.
I got 49.92.
You did 0.0416 times 1200. And you got 0.49?
49.
49? Well, we've done something wrong somewhere then. Let's check this one again. 0.0416 times 600. What's it?
When we do the, both resistors divided by voltage, I get 24.
0.0416 times 600 was 24.96.
Okay, so here's our issue. The voltage drop of this one is wrong. 24 point what?
96.
96. So we'll just say 25. Okay. 25 volts. That gives us how much volts over here? 50. And then this one's gonna be 50. And what you said it come out to be 49 point something, right? When you did this. Now we're sounding more right. Okay. Now, what's gonna happen? I'm gonna throw another resistor in here. And it's gonna be 300 ohms. So this changes everything again, right? Changes my voltage drops, changes my current flow, and my total resistance. What's my total resistance now?
21, right?
2.1K. All right. So what's my current flow? 35.7 million. Did you calculate that? Or did you do it in your head? Oh, I didn't see your phone. 35.7 million. I was fixing to be impressed, dude. Seriously impressed. Okay, now, what's my voltage drop at R1? How would I do that? How would I calculate that?
Current times resistance.
Current times resistance. Anybody?
21.42.
21.42. All right. So that means I got how much volts right here? 53.6.
53.58.
53.58, huh?
I think it's.
53.58, I think.
Yeah, that's what I got.
Okay. All right. That means what? That the voltage drop of this, well, no, this ain't gonna be zero no more. It's gonna be different, right? Because we got this resistor here now. So what's the voltage drop of R2?
It's gonna be double, what, the first one?
It is actually gonna be double that one, right?
Right.
You can do that,
42.84.
42.84. All right, good. All right, so what's the voltage here now?
26.79.
No, it's gonna be like
11
or 10 and some
10
change.
something, yeah.
Yeah.
What is it?
I see what I did.
10.74.
10.74. What's the voltage drop of R3?
0.
Oh.
10.7.
It's gonna be 10.74. If you do 35.7 milliamps times 300, it should be right there around 10.74. See how it balanced itself out and it still equals 0? It shared the load, it shared the voltage on all three resistors that time just by adding. We didn't change the resistance here or here, we just threw that one in there. And it reacted, the current reacted to that, so that made all the changes, okay? Okay, so let's leave this right here. We can go out here and build this, and we're going to measure the current, and we're going to take the voltage readings and see if it should be pretty close. Okay, that is the first thing we need to do. We need to set the proper voltage.
34.7 is the
Current. All right, so let's get the voltage on there. So we're going to set our meter on volts DC.
75 volts.
I'm going to measure it right here. We'll turn it up to 75.
How high does that power source go?
120. The DC so it does.
That's cool.
Okay, y'all see the voltage there? 75. All right. So now what I'm gonna do is I'm gonna turn this off since we got that set. I'm gonna put this over here in my amp jack. Put it on amps DC. And I'm gonna take this wire right here out.
So that'll act as a
So this is gonna act like my wire so I can measure the current. And y'all said it should be 37.5, right?
Yeah.
Okay.
37. Yeah, 37.
35.7 million. So this should read 0.035,
Yep.
36, somewhere around there. Okay, so we're gonna measure here to here. And y'all look at it, see that? 0.36, okay? So right where our calculations were. Now, let me put this back in. I was just showing you that's the current, right? Now, let's do our voltage measurements. Flip this back. Put it on volts DC. Check my applied again. It's 75. Yep. All right. So what did we say the voltage drop of resistor 1 was going to be?
21 and some change. It should be down to 53.58.
2142. So 21 and a half around about. So if I measure across resistor 1, it should read about that much. Okay. So if I measure across it, 21.57. See that? Okay. So one thing also, what did we say the voltage will be on this side?
53.58.
Okay, so if we measure from 0 to here, it should read about that much. Okay, so let's see if it does.
Yep,
See that?
that is cool.
All right. Now what's the voltage drop of R2?
42.84.
42.84. So if we go across it, remember how I was telling you it reads the difference of potential? All right. 42.84. Look at that. All right. Now, think back to, what was this reading right here?
53.58.
Okay. What's the reading right here? What's it supposed to be?
10.74.
Okay, so 0 to here, it's reading 11. Okay. So 11 minus 53 is supposed to be the voltage drop across this, right?
Yeah. 42, yeah.
42. Okay. all right? And then the voltage drop in my last one will be whatever my potential was right here, right? 11 point is what I'm reading, but y'all said 10 point.
Yeah.
Okay, so. Here it is.
Zero. Oh, yeah, that's right.
And if you think about it, I'm reading the same thing right here to here, because look, this is the same wire as right here. This is the same wire as right here, so it's the same as reading across. Okay. That's it. Cool, huh?
Yeah, it is cool.